Uh, Good afternoon, everyone. I want to welcome you to my lecture today. Of course, today we're gonna start a new chapter that we actually call. Sorry, can you hear me? It's time for lecture. Okay, so like I said today, we're starting a new chapter that I actually call fundamental sampling distributions and data descriptions. I think we are gradually getting to a topic that actually make more sense, when you want to talk about research. All what I need from you is to pay attention and ask questions where necessary. And I think to also tell you, I'm going to be recording my lectures from now. And I'm going to put the recordings on YouTube. The moment you put my name on YouTube, of course, you're going to have access to the recording. That will give you another opportunity to be able to catch, if you miss something in class. But make sure because I put not only for this class on YouTube, I also put some higher level statistics. So make sure it is for your class, okay? Okay, now in the outline, we're gonna have what we call introduction to random sampling, and I'm gonna discuss bias and variance. Okay, please, I need you, like I said, to pay attention to what we want to be doing. But before I go into random sampling, I think I need to first have maybe to retrace our step back to what we want to do now. Why are we doing what we're doing now? How do we find ourselves in a situation where we needed to take a random sample? Please, I need you to pay attention. I'm going to give you the history. I'm going to give you the background for you to be able to understand why are we doing what we want to do now. Okay, the fact remains that the existence of reality is independent of human knowledge. Existence of reality is independent, of human knowledge. So what I mean is the existence of the physical world is independent of human knowledge. And as human beings, we actually want to understand our environment. I want to have an understanding of my political environment. I want to have an understanding of my medical environment. I want to have an understanding of social environment, psychology, and so on like that. And if I want to understand my environment, then what I need to do, it means I actually need knowledge. I need knowledge. I'm seeking for knowledge to be able to understand what happened around me and where the knowledge is going to come from. Where the knowledge is actually going to come from the information I got. Okay, the information is going to come from where? If information is actually going to come from data, take a look at that. Information is going to come from data. You know, when we collect data, the information that we're looking for is not readily available in data unless something, you have to do something before you're going to have access to the information in the data. And what you need to do is we actually need model. We need this guy. We need model. Okay, there are different kind of models around. If we're using the best model, we'll be able to get information hidden in data. Okay, we believe information is hidden in data. Now, when we want to collect data now, okay, maybe what do we want to collect data on? At times, we may be seeking information about maybe what is the average household income in this country or in a particular country. Or maybe I want to compare the standard of living between two countries. Or I want to compare maybe the proportion of females in the United States Congress and the Canadian Parliament. Or maybe I actually want to figure out what is the proportion of citizens of a country that approve the job the president is doing. All of that, we call that parameter. Okay? Parameter is, a population characteristic value that we seek to determine. Okay? A population characteristic value that we seek to determine. I just told you now. Parameter could be mean, could be variance, could be standard deviation, could be proportion, could be difference of means, could be difference of proportion, and so on like that. But you know what? If we want to get parameter exactly, we need the whole population. But you know what? Because we're limited by budget, okay? We're limited by budget. We do not need to study the entire population. All what we just need to do is to take a sample. A sample is a fractional part of a population. But let me tell you this. If you want to take a sample from the target population, then you got to ensure that the sample you're going to choose should be a random one. Does that make sense? What do I mean by random one? It means you're giving equal chance to every element in the population. And if you do that and choose a sample, then your sample is going to be a representative sample. Does that make sense? So when I talk about random sampling now, okay, before we can make a judgment, before we can make an inference, okay, because what the idea behind statistical inference is to make a judgment, okay, is to generalize on the entire population based on sample information. That's what we do all the time in research. When you conduct research, you take a sample of individuals and you generalize the result on the sample on the entire population, but before that your generalization is going to be fantastic, then you have to take a random sample. Does that make sense to everyone now? That's what I mean by this. And that was why I said, thus we must make sure that the samples must be good representative of the population. And we have to pay attention to what I call sampling bias and variability. So because of that, I'm actually going to explain two things that are very, very important. But before I go into that explanation, I believe you understand the reason why we're doing what we're doing. We want to understand our environment. We need knowledge of our environment. It could be political environment, it could be medical environment, it could be social environment, whatever environment, we want to have an understanding. And you can only have your understanding of environment if you get information. Information don't come easily, something needs to be done. Okay, information is going to come from data. When you collect your data, you don't have access to the information immediately unless you make use of a model. We're going to make use of a model to be able to get the information that we need, okay, from data. And when I say information, that is exactly parameter. You know, that was why I said the population characteristic value that we seek to determine. Okay, now which means at the end of the day, we actually, if I want to figure out parameter, now I'm going to take a sample. And you know, if I want my sample to be a very good representative of the population, then I need to apply what I call the principle of randomization. Okay, we take a random sample. Okay, if we don't take a random sample, there's going to be an issue. Okay, now, and you know, if I want to ensure validity of statistical inference, when I say statistical inference is about making a judgment. Okay, you actually want to generalize a population based on sample information. But if you want to have a very good generalization, then the mode of sampling matters. The way you take your sample from population matter, which means you got to make sure everybody in the population has equal chance of being selected into your sample. Because of that, I'm actually going to show you a picture right now. But for this picture to make sense, I'm actually going to tell you there are two things that we need to pay attention to. Okay, if you want to ensure validity of statistical inference, it's actually what we call bias. Okay, we call it bias-variance tradeoff. Okay, let me first give you the definition of bias. What do I mean by bias? What do I mean by variance? Please pay attention. If you don't understand, ask question. Okay, you know, is a way of simplifying assumptions by model, okay, in order to make a target function to be easily approximated. Please, I need you to pay attention. I need you to pay attention now. Okay? You know, when I say bias, you know, I told you the other time, right? We actually need, if I collect data, to be able to have access to the information in the data, I actually need model. Okay? Now, what do I mean by model? A model is a mathematical representation of reality. Because we live in a mathematical world, we can actually depict reality by mathematical equation. So, model is a mathematical, maybe I'm going to say mathematical or statistical simplification of reality. Okay, now the model is going to be a mathematical form. That is why most of what we've been doing in this class, you're going to see equations, right? Okay, those equations, they depict reality. Okay, now, like I said, We want to use model to depict reality, but let me tell you this. Model is not the same as reality. Okay? Model is not the same as reality, which means model can only give us an approximate reality. Does that make sense? Model is not the same as reality, and the reason why model is not the same as reality is because there's always going to be error. No matter how we try, there's going to be error. And because of that, if we want to use model, we're actually going to have assumptions. If you want to use model, we're going to have assumptions on the model, and the assumptions will revolve around error. Does that make sense? So, by bias, it's a way of simplifying assumptions. By model, in order to make a target function to be easily approximated, because let me tell you this, if I want to depict reality, I actually need a target function. Oh, at times you see in binomial, you see f of x equal to this. In approximate f of x, you only see function of x. That's a target function. That's a target function. So that is what we call, so let me now tell you this. In scientific community, bias is an issue. It's a worst enemy of economists, psychologists, statisticians, and so on like that. Okay, because of what? Because of the fact that this bias, okay, is come with the error, which is like distance between prediction and a target value. There's always a distance between prediction and a target value. I told you there's always going to be error, right? Because there's a distance between prediction and a target value. Okay, now, so bias induce error. Okay, but let me tell you, what kind of bias that induce error is I bias. I bias. I bias. And I'm going to tell you the meaning of the high bias. What do we mean by I bias? High bias. Okay, I'm going to tell you the meaning. Let me just tell you the ideal situation. We can't do without bias. We can't do without variance. But the ideal situation, we want the low bias and the low variance. But I first want to talk about high bias before I'm going to go into the variance. Now, when I talk about high bias, maybe you are actually using oversimplified model. Maybe you have a complicated situation, right? And you're using a simple model. Using a simple model for a complicated situation, it means you actually pay more attention, okay, to the, you didn't really pay attention to the model. You pay more attention to the training data, okay? And at the end of the day, high bias will induce an error. What kind of error is it going to induce? It's going to do underfit. Your model will be underfit. Underfit. Your model will be underfit because you are using a simpler model for complicated situations. Does that make sense? Okay? Now, like I said, you're using, which means that very model will not be able to learn the pattern. You'll not be able to learn the pattern in the data. You'll not be able to learn the signal. Okay? That model will not be able to learn the relationship if you are actually talking about maybe relationship between variables because the model is under fit. Okay, like I said, bias will lead to underfitness. And it's in scientific community, that is the reason why we want to try as much as possible to use a complicated model. But let me tell you this. If I want to, solve this problem now, and I decide to use complicated model, then I have to be guided in such a way that I don't use a more complicated model for simple situation. Do you know the problem here under fit, bias, because you are using a simple model for complicated situation. If you now make an attempt to make your model complicated, so you need to be guided in order not to run into a problem of high variance. Now, by the way, what do I mean by variance? Okay, variance, on the other hand, is the amount of change, the amount of change, or let me just say the amount, let me put it this way, the estimate of a target function, changes, changes given different training data. Here we are talking about sensitivity of your model to a new data point. So the amount, that estimate of your target function, changes given a different training data. That is what we call variance. If it changes so greatly, that's an issue. So, and that is why we see, variance tell us how spread, right? The variance tell us how spread. Now, let me tell you, variance also come with error. The same way bias come with error, but here I'm going to be talking about when you have high variance. What does high variance means? High variance actually means you are using complicated model for simple situation. Does that make sense? Which means you pay more attention to the model instead of the data, more on the model compared to the data. You know what is going to happen? Your model will perform greatly with your data, but will perform poorly with unseen data. I'm going to say that again. High variance lead us to overfit. High model will lead us to the problem of overfit. Overfit. That's what we call overfitness. Why? Because instead of your model to learn only signal and pattern from the data, but your model memorize it. It memorizes the data. Which means your model will only perform great on that data alone, and your model will not be able to perform on a new data set. Tell me, what is the essence of a model? A model should be able to perform not only on the training data, it should also perform on the test data, on the new data. Does that make sense? So that is what we call high variance. And let me tell you this. If you really want to, and let me now show you here. Take a look at the first picture. The first picture, where is my target? My target is in the middle, right? My target is in the middle, right? If you take a look at this, if you take a look at, let me just show you this. Give me 1 second. If you take a look at this guy, all those dots, they are clustered, right? Oh, because they are clustered, it means they have low variability. Low variance but high bias because that is far away from the middle. And that is why the first one is not a good deal. High variance, low bias. High bias, low variability. We don't want it. Let's go to the second one. Oh, look at the second one. The second one is very close to the middle, but except that they are dispersed. Low bias, high variability. Let's go to C. Oh, this is the worst one. High bias, high variance, but this is the ideal situation. This is how you want. Low bias, low variability. Okay, so when we're conducting our research, we need to be able to, do it in a way that we actually are going to have a kind of a balance, trade-off, between the tension curated by bias and variance. Now, I just gave you the definition of bias, okay? And I said any sampling procedure that produces an inference that consistently overestimate or consistently underestimate. Okay, for instance, you want to get the average in a particular, maybe you take a sample. If I want to get the average of the amount of money spent by college students, and if I did not actually take a random sample, if I only choose those ones that I like, there's possibility my results may be misleading because of the fact that the sample that I choose is not a representative sample. Okay? So we don't want a situation where we're going to have a biased result. Okay? You can see that we don't want to overestimate. We don't want to underestimate. We want to be somewhere in the middle. Does that make sense? We want to be somewhere in the middle. Okay. Now, what do we now need to do? Since we know bias is a problem, I think I've told you what you need to do. If you want to eliminate bias, then you take a random sample in your research. Does that make sense? You take a random sample. And that was why I said to eliminate the possibility of bias in sampling procedure, then you got to choose a random sample. Okay? And when you choose a random sample, then you need another assumption. The random sample will guarantee that observations are independent. In this class, we've done independent, right? Okay. Now, that is it. Now, if that happens, then we can actually have this that we've done before. You remember that? When we're talking about when x1 up to xn, x1 up to xn, maybe the x1 here. If I take a sample, if I actually want to investigate the average amount you spend per week, okay, and I choose a sample. X1 here may be the response from one person. Oh, I think I spent $200 a week. Another person, I think I said $100 a week, and so on like that. Now, I expect that the probability of the joint occurrence of x1 to xn should be equal to the product of each. What assumption am I using here? Independent assumption. Does that make sense? Okay. Now, we now want to go to some important statistics, like if I have data set. Let me tell you this. Statistics is divided into two. We got statistical, we got descriptive statistics, and we got inferential statistics. Okay? We got descriptive statistics, and we got inferential statistics. Okay, so what I want to first talk about is like descriptive statistics. Okay, this is what I call some important statistics. Like I want to talk about measures of location. If I want to talk about average. Oh, we got three measures of that. Mean, median, mode. How do we compute mean, median, mode? Okay, and what do we use mean, median, mode to do? Oh, well, I'm looking for a data point that will represent the rest. That's why I have to go for them. Okay, then I need a function. I need a target function. This is my target function now. Can you see that? That is my target function. You remember the other time, we said we needed a model, okay? We need to have a simplifiers option so that our target function will actually be very easily to, very easier to approximate. Now, if I want to compute the sample mean now, if I want to do the sample mean, I've taken a random sample, okay, and I want to find the mean, okay, then I'm actually going to add the responses together by divided by the number. This is the formula that I'm actually going to use. This is what we call measures of location. There are three measures of location: mean, median, mode. They are important statistics. They all fall under descriptive statistics. Look at the word descriptive. I'm describing, I'm summarizing my data, but I'm not making a judgment. This is not making judgment. Because making judgment fall under statistical inference. But what we're just doing now is just to describe, just to summarize our data. Okay, so if you look at example 8.1, you have a data on weight. Take a look at that. The weight of a group of students, okay, in our LBS are given below. You got from 135 to that. This depicts reality. There's a variation here. Okay, this the student choosing here, they don't have the same weight. Look at 135 different from 105, different from 118, and so on like that. This is a variation, right? Okay, now find the mean. You want to find the mean. Okay, if another student joined the group and his weight is 250, what would be the new mean? Okay, of course, if you want to find the mean here, you're actually going to use the formula here, finding the mean. All you just need to do, add them up and divide by the number of observation. Okay, so that is what you're going to do. And of course, if another student join, what is going to happen? If another student join, the number of the sample is going to increase by 1. Don't forget, you're actually going to add them up and divide. Okay, now let me tell you this. There are 3 measures of location. If I want to figure out average, there are 3 measures. I could use mean, I could use median, I could use mode. But what is the condition under which I'm going to use mean? Is there anything I need to put into consideration before choosing mean or median or mode? I think the major thing to put into consideration for you to decide between mean, between mean, median, and mode is the distribution of your data set. I'm going to say that again. What you need to put into consideration if you really want to choose between the mean, median, and mode is the probability distribution of your data set. Okay, now of course we got a way to figure out the probability distribution of the data set. If the distribution of the data set is normal, of course we've done normal distribution, right? Then any of them can be used. We can use mean, we can use median, we can use mode, but the best is going to be mean. Does that make sense? I'm going to say that again. What determines the choice? Okay, I told you we got 3, right? Mean, median, mode. Because the 3 of them is used to figure out the average. They are measures of location. We also call them of central tendency. But what determines the appropriate one to use is actually probability distribution of the data set. Okay, so like I said, when data set follow normal distribution, okay, the mean, median, and mode, they're going to be very close. But the best is mean. Does that make sense? Okay, we have another one called median. Of course, the median is, of course, you need to first arrange your data point in either ascending order or descending order. Then you're going to choose the middle one if you are working with the odd number of observation. But if you are dealing with the even number of observation after arranging them in ascending or descending order, you're actually going to take the 2 in the middle, you add them up and divide by 2. Okay, now take a look at example 8.2. The weight of a group of students, given that, find the median now. Okay, what I need you to do, you can compare your results. When you find the mean, I think it's the same data set. When you find the mean, when you find the median, you can compare results. Does that make sense? But let me tell you this. Let's say in this data point, I included this. $6,000. Take a look at that. If there's 6,000 among this, then that's going to be called an outlier. Outlier, according to Benkamp in 1982, an outlier is a data point that is not consistent with the rest. And that data point will be problematic to the model. If I want to find the average here and I use the mean to find the average, then I will overestimate. You remember the other time we talked about overestimation, underestimation. So now we got to take care. We actually need to use a measures of location, okay, that could ignore the potential threats. And in this case, the median will be reasonable. Because if I want to use the median, I'm actually going to arrange this observation in either in ascending or in descending order. Of course, that extreme value will not be in the middle. Does that make sense? So, which means in a situation where the probability distribution of the data set is not normal, then the median is a very good candidate. Because the median is not sensitive to outlier. Because what induces skewness is an outlying point. If you got a point that is not consistent with the rest. Now, another beautiful example is the mode. A mode is, put into consideration the most frequently occurring data point. Which data points occur more frequently than other data points. Okay? Now, do you know you can be given some set of data and we ask you to find the mean, median, and mode, compare them. But at times we could have issue with mode. You can look at a set of data, there's no mode. There is no mode in a situation whereby none of them is repeated. Let me see, if you take a look at A, is there any data point repeated? Can we check that? Is there any data point repeated? Then in that situation, there's no mode. At times, mode may not exist. And at times, we could have more than one data point that could be mode. Situation where you have more than one data point that is a mode, that's a problem. Does that make sense? And that is the issue with mode. Okay, mode may not exist. Even if it exists, it could be more than one. If it is more than one, we're going to call it bimodal. Bimodal. If it's just two, bimodal. If it is more than two, we're going to call it multimodal. Whether bimodal or multimodal, oh my God, that is problematic. Does that make sense? That is the issue with mode. And that is the reason why most of the time, what you normally see is mean. But before you can use mean as a measure, you got to make sure the distribution of your data set is normal. Okay, of course, we have a way to test for that. Okay, now, after that, the next thing we want to talk about is, statistics is like a story that goes on and on and on. Now, we actually, when you make use of the mean, or you make use of the median, or you make use of the mode, which means you are picking a number that represents the entire data set. And how am I going to know if that particular data point, if that result that we arrive at is actually reliable? Then I need to investigate variability. Does that make sense? I remember the other time when I was defining the variance. Take a look at the variance. The amount of estimate of a target function changes given different training data. So if I want to know the spread, if I want to know That is problematic. Does that make sense? That is the issue with mode. And that is the reason why most of the time, what you normally see is mean. But before you can use mean as a measure, you got to make sure the distribution of your data set is normal. Okay, of course, we have a way to test for that. Okay, now, after that, now, the next thing we want to talk about is, statistics is like a story that goes on and on and on. Now, we actually, when you make use of the mean, or you make use of the median, or you make use of the mode, which means you are picking a number that represents the entire data set. And how am I going to know if that particular data point, if that result that we arrive at is actually reliable? Then I need to investigate variability. Does that make sense? I remember the other time when I was defining the variance. Take a look at the variance. The amount of estimate of a target function changes given different training data. So if I want to know the spread, if I want to know how reliable is the data point, okay, that we arrive at, whether by means of computing the mean or median or mode, okay, I think it becomes necessary to investigate how far apart, if these are the data point now, if these are the data point, okay, if these are the data point and I compute the mean, in fact, the mean may not even be member at times. You know that? The mean, the value you got may not even be members of the group. Now, let's say this is the value. I'm just assuming now. Okay. Now, how can I trust this value now that we got? Is to measure how far apart is the mean from the respective observation. Does that make sense? How far apart is politics, going into politics now? This guy is the one representing my consistency. Okay, this is my consistency, right? We've chosen this guy. If you really want to know, for this guy to be a very good representative, it shouldn't be far from us. He should not just stay in Washington all the time. He needs to come, like, organize a town meeting, meet with the people in the constituency. Okay, what is going on? What do you need? Stuff like that. That's what we mean. So the closeness, we need to be able to investigate the closeness of the mean to the respective observation. If I want to do that, then I actually want to talk about variability. You see, we don't just do what we do. There's a reason why we do what we do. Does that make sense? So we want to come to variability now. The variability is just to measure how far apart. We're trying to see whether the value that we got for mean is actually reliable. But let me tell you this. We got different measures of variation, and the one to use depends on the probability distribution of the data set. The other time, for us to be able to go with the mean, the distribution was normal. If I use mean and the distribution is normal, if I want to measure variability, then I'm going to be talking about variance, standard deviation, range. Does that make sense? That is going to be the measure. But in a situation where the probability distribution is not normal, then I can use variance. You know why? Because variance is sensitive to outlier. If variance is sensitive to outlier, standard deviation is also sensitive because the standard deviation is the square root of variance. And range, what do we mean by range? Range is the difference between the highest and the lowest. Range is another measure, which is the difference between maximum minus the minimum. Range is also sensitive to outlier because if there's an outlier in your data set, it's likely going to be the minimum or the maximum. Does that make sense? Okay, now let me talk about the variance now. This is the formula that we use, for variance. You can use a calculator to compute all of that. And don't forget, the square root of the variance is the standard deviation. Okay, but let me tell you, why do we use standard deviation? Can somebody tell me? Extra credit. Why do we prefer using Standard deviation to variance when we want to figure out how reliable is the mean. Why do we prefer standard? Go ahead.
Isn't it just a lot easier, less calculations, because we know like approximately what percent are within one standard deviation, two standard deviation?
You're very close. Not how easy is that. Because just take a look at it too. Look at the difference. Variance, standard deviation. Go ahead.
Variance is like a double power. It's a second power, right? Variance is always square.
Okay.
But standard deviation itself is the nearest approximation to mean.
You are close. You are more closer. Go ahead.
Is it because like standard deviation is more of a direct measurement? It's because it measures like just kind of like the distance the data has rather than like adding any kind of like on top of what he was saying. It's not looking at the distance squared each member has from the mean, but rather just the variance or the deviation in and of itself, like more direct.
More closer. More closer. Thanks for sharing. More closer. Go ahead.
It's best at finding the center of a sample.
The what?
It's the best at finding the center of like a sample.
Yeah, I know it's the best, but how? How is it the best? Oh, because you are very close. Because the variance is measured in square units, but the mean is not measured in square units. You understand what I mean?
Yeah.
Variance is in square unit. How is it in square unit? So look at that. Summation. If you take a look at this guy here, you see that? The deviation squared, right? Which means variance is in the square unit, but mean is not in square unit. Therefore, variance is not going to be a good measure. Then what can we do to variance? In order to have the same unit as the mean, then I'll take a square root. When I take a square root of a square unit, what happens? It automatically becomes the unit of the mean. Does that make sense now? You are all close. Good job for sharing. Okay, now you see why, but there is no way we'll be able to get to the standard deviation without passing through variance. Does that make sense? Okay. Oh, that is my lecture. Now take a look at this. The standard, now, at times you're going to see in the formula for variance or for the standard deviation, the formula will be divided by n, another one divided by n minus 1. They are not the same. Please pay attention. Pay attention. When you are using the formula divided by where you see n minus 1, that is for the sample. Like here now, this is sample standard deviation. That is the sample variance. But if I'm dividing just by n, like this, then I'm no longer focusing on sample. I'm focusing on the entire population. Does that make sense? Where the n, an uppercase n, in this case now, is actually going to represent the population size. Does that make sense? So when you are dividing by n, okay, then you're actually telling the world using population data. Okay, now example 8.4. Calculate the sample variance and the sample standard deviation of the following. Look at the word sample. Okay, all this can be done, if you want to follow the formula. The sample variance, the meaning why we're doing sample variance, sample standard deviation, we actually want to tell how reliable is the mean. Because the more the value of the variance or the standard deviation, then the less is going to be the degree of the reliability of the mean. Lastly, I told you, another measures of variation is range, where in the data you just need to identify what is the maximum, what is the minimum. But this is not a good measure if the distribution of the data set is skewed. Okay? So if it is skewed, okay, I cannot use this. I cannot use variance. I cannot use standard deviation. I want to award an extra credit now. What am I going to use then as a measures of variation? Like if the distribution is skewed. Go ahead. No, I mean measures of variation. Median is going to be the measures of location, right? That's correct. But as a measures of variation now, since I cannot use range, I cannot use variance, I cannot use standard deviation, there's another thing we can use for a situation where distribution is skewed. What is that? Eh? No, mode, see, mean, median, mode, they are all measures of a location. But right now, I'm talking about measures of variation that can be used. You know, I told you can use range, right, to measure variation. You can use standard deviation. You can use variance, okay? But all these are applicable, they are appropriate when the distribution is normal. What of in a situation where the distribution is not normal, there's an outlier, and you computed the median, okay, and what you want to check for the variation. Can somebody tell me? You say what? Whether we should use it, but you are very close. There's one time that it is called, you've heard about it before in high school. You've heard about it, it's called in high school. We call that interquartile range. Have you heard about interquartile range? Have you heard about this guy? Which is called Q3. Have you heard about quartiles? Right? It's also a way, that's a measure of variation. We use interquartile range as a measure of variation when the distribution of your data set is not normal. In that situation, you need an upper quartile and a lower quartile. Okay. Before I go today, the midterm 2 will not focus on this topic that we just started today. I put it on the announcement section on Wednesday. Check the announcement section to see the areas that will be covered in the midterm 2. And for the midterm 2, we're not going to write, there's not going to be an in-person exam. It's going to be on quiz, online. You can be anywhere in the world to write it, but you need to log on to Zoom. It's going to be during the exam time. I'm also going to be on the Zoom monitoring the way you're doing it. Does that make sense? Okay, make sure you stay safe and enjoy your weekend. Bye for now, everyone.